Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. You know, compact Hausdorff spaces are normal, but today in this clip we will establish some results which will force to conclude that unlike compact Hausdorff spaces, locally compact Hausdorff spaces are not normal in general. So let's start with a simple result which says that simple result is this. Let X be a topological space. X be a topological space. Okay, and it can be expressed as X equal to this union a lambda in capital lambda, where all a lambdas are open in X. Okay, now we will show that a subset B of X is open respectively closed if and only if each B intersection A lambda, okay, that is the portion of B which can be viewed within A lambda, is open respectively closed in A lambda for all lambda in capital lambda. Okay, so let's prove this first. Okay, case of the proof. Okay, one part is very easy. Okay, because if this B is open respectively closed, then this closed means in X, of course, in X. Okay, then this B intersection A lambda, by definition of subspace topology, B is open, so B intersection A lambda is open in A lambda, and if B is closed, then B intersection A lambda will be closed in A lambda. So then this is open respectively closed in A lambda for all lambda in capital lambda. Okay, it comes from the very definition of subspace topology, straightforward. Okay, so this part is very easy. Next part is also very easy. So converse part. Okay, first of all, we consider that this B intersection A lambda is closed in A lambda for all lambda. Okay, so let B intersection A lambda is closed in A lambda for all lambda in capital lambda. Okay, fine. Therefore, A lambda minus B this is open in A lambda, isn't it? We are considering that B intersection A lambda is closed in A lambda. Look at this picture here. So this is say X, and say this is one A lambda. Okay, now say this is B. Now this B intersection A lambda is closed in A lambda. This is closed in A lambda. Okay, what does it mean? That is, this A lambda minus this B, that is this portion, this complement of this is closed in A lambda. So this portion is open in A lambda. What is this portion? This is A lambda minus this B. So A lambda minus B is open in this A lambda for all lambda in capital lambda. Okay, fine. And A lambda, these are open, given this X is union of this A lambda, where all A lambdas are open in X. Fine. So this is open in A lambda and A lambda open in X. So this is also open in X. This is open in X for all lambda in capital lambda. Okay, so their union A lambda minus B, their union, this is, what is this? This is equal to union of A lambda minus B, that is X minus B is open in X. Okay, so X minus B is open in X, so B is closed. So B is closed in X. Okay, so if every B intersection A lambda is closed in A lambda, then B is closed in X. Okay, if all such intersected portions closed in A lambda, then this B must be closed in X. Mind it. Okay, so we have proved this result considering that each B intersection A lambda is closed in A lambda. Now I will prove that if each portion of B within A lambda is open in A lambda, then B itself open in X. It is also very easy. Also, now let B intersection A lambda is open in A lambda for all lambda in capital lambda. Then B intersection A lambda, this is open in A lambda open in X, so this is open in X for all lambda in capital lambda. Okay, so their union, B intersection A lambda, lambda in capital lambda is, what is this? What is this? This is obviously B intersection union of A lambda. Union is distributive, isn't it? Over intersection. Let me write this. So this is B union A lambda, B intersection union of A lambda, no? Lambda in capital lambda. What is this? This is B intersection X, because this union is whole X in the statement. X is union of A lambda. Fine. So since every B intersection A lambda open in X, so their union also. What is this? This is actually B intersection X means B. This is open in X. This union of open set. Okay, so if B intersection A lambda is open in A lambda for all lambda, then B is itself open, and if this B intersection A lambda closed in A lambda, then B is also closed. If X is written in this way, union of A lambda where A lambda is open for every lambda. So this is the first result. Okay, today's first result. Okay, so this is very important. I will use this result. Just wait. Now the next result is very interesting result. Actually, it will show how locally compact subset of a Hausdorff space looks like. Okay, so the second result of this clip is this: a locally compact subset, a locally compact subset, say B, of a Hausdorff space X is of the form this B equal to O intersection C, where O is open and C is closed. C is closed in both in X. Okay, so a locally compact subset of a Hausdorff space X is of the form this. Okay, it does not mean that any subset of the form this of a Hausdorff space is locally compact. Okay, but a locally compact subset of a Hausdorff space X will be of the form this. So let me sketch the proof. Sketch of the proof. Fine. So here B is locally compact subset of a Hausdorff space. So B is also Hausdorff, because Hausdorff property is hereditary property. Fine. So B is actually locally compact Hausdorff space, and we'll see that it will be of the form this open intersection closed set in X. Fine. Okay. Since B is locally compact Hausdorff, right? Locally compact Hausdorff. So every point of B has a relatively compact neighborhood in B. In B is important, because the underlying space may not be locally compact. It is not given. Okay, but the subspace B is locally compact Hausdorff. So we are now in B. Since this is locally compact Hausdorff, every point B in capital B has a relatively compact neighborhood, say capital N. In B is important. In B. So neighborhood in B. So there exists an open set in B containing B and contained in this capital N. But open set in B means open set in X intersection B. Okay, B is a subspace of the space X. Okay, so there exists an open set say VB. I am just using this B as index because for every B we will get such an open set. Okay, so it depends on B, that's why. So there exists an open set VB in X so that this X belongs to this VB intersection B. This becomes an open set in B and it is totally contained in N by the definition of neighborhood in B, obvious. Okay, and not only that, N is relatively compact neighborhood. Okay, so this in this and this closure of this set N, closure of this set N of this neighborhood N in B is compact by the definition of relatively compact set whose closure is compact. Okay, we are totally confined within B now. Okay, till this we are doing everything within B, and this closure in B of N is compact. Fine. Okay, since this closure in B of this set VB intersection B, I said in the last clip, this equal to just closure of B small b, no, closure of this in the main space, mother space, whole space X intersection B. Very easy. This, so if you take closure of this, it will be subset of closure of N in B. Okay, and it is compact. It is compact. Fine. So this is a closed set, okay, of a compact subset. This is closed in B, mind it. Okay. Okay. So since this is compact, okay. What is this? Since this is a compact subset, the closed subset of this, so since this, then what will happen? This closure of this BB intersection B, this is compact. This is compact. Okay, fine. This is compact subset of the main space is Hausdorff of the Hausdorff space X. Okay, since this is a compact subset of the Hausdorff space X, and hence this closure of B small b intersection B is compact subset of Hausdorff space is closed. This is closed in X. Now here in X now. Fine. So this BB bar intersection B, this equal to this. Okay. This is closed in X, that is this BB bar intersection B is closed in X. Fine. And all those things is happening for every B in B. Okay. Now let O equal to union of all those B in capital B. What is BB? BB open set in X. So O is the union of all those open sets. So O is open, and every VB contains B. So whole capital B will be contained in O. Let this, then this O is open in X, and this capital B, no, not capital B, no, right, capital B contained in O. Okay, fine. Now let me calculate this. Let me rewrite this VB intersection B in some another way. It can be written as VB intersection VB bar. VB bar is larger than VB, so it will be again VB intersection B, and intersection is associative, so we can write this. Okay, fine. Now from this expression of this VB intersection B, we can say this VB intersection B is closed in X. We know VB bar intersection B is closed in X, but not only that, VB intersection B also closed in X. How? Because this VB bar intersection B is closed in it, so this is closed in X. Okay, so this is closed in X intersection VB. Oh, so this is closed in VB, closed in VB, not closed in B. So this implies BB intersection B is closed in VB, and it holds for all B in capital B. This is important. So here we see that O is written as a union of open sets in X. Every VB is open. Every VB is open set in X. Every VB is open set in X. Okay. So concentrate in this portion. This O equal to the union of VB, where every VB is open in X, and this B intersection VB is closed in VB for every B in B. Okay, fine. So since every VB intersection B is closed in VB, so by the previous result, by this result, just few minutes back we have proved this X union of this A lambda, where A lambdas are open in X, and this B, if B intersection A lambda closed in A lambda for every lambda, then B itself is closed. Here same thing. O is playing the role of X in the result. Okay, so this O equal to union of this, and this B intersection VB is closed in VB for every B. So B itself will be closed in O. In the result, B was closed in X because here it was X. So here B is closed in O. So this B is closed in O. Closed in O means closed in O. So B is closed in O. That is B equal to O intersection A closed set in X, because closed set in X intersection O is closed in O. So B being closed set in O, so this implies B equal to O intersection, this is closed in O. So closed set in X intersection O, so C, where C is a closed set in X. So here we see that O is an open set in X and C is closed set in X, and O intersection C is B. So we are done. So B equal to O intersection C, where O is open in X and C is open in also closed in X. Okay. So B equal to O intersection C, where C is closed in X and O is open set in X. So done. So this is the second result. Now the third result, and this is also very easy. Actually, this result will characterize local compactness of a subspace, of a locally compact Hausdorff space. Okay, so the next result is a subspace B of a locally compact Hausdorff space, locally compact Hausdorff space X is locally compact if and only if it is of the form this B equal to O intersection C, where O is open in X and C is closed in X. Okay. Have you seen the difference between the earlier result and this result? In the earlier result, the underlying space X was just a Hausdorff space. Now this X is locally compact Hausdorff space. Okay. So in this result, the underlying space X enjoys more properties than the earlier result. Okay, so and we are getting something more. We are getting now if and only if. Okay, it will give you the whole collection of locally compact subsets of a locally compact Hausdorff space. So let me sketch the proof. Sketch of the proof. Okay, one part is very easy here also. Okay, because if B is a locally compact subspace, then what will happen? If B is locally compact subspace of this X is Hausdorff of this locally compact Hausdorff space X, then just if we use this property, the B is locally compact subspace of Hausdorff space X, then by the previous result B will be of the form O intersection C by the previous result, where O is open and C is closed in X. Okay, so in this part, this local compactness of X is not necessary. But in the converse part, we have to use this local compactness of X. So converse part, that is, we will assume that B is of the form this O intersection C, open set in X, C is closed set in X, and then we will see that this B is locally compact. Okay, so we have to show B is locally compact. Okay, so we have to take any point from B and we have to find a relatively compact neighborhood of that B, isn't it? Because this B is Hausdorff, because the main space, the underlying space, whole space is Hausdorff. So B is Hausdorff. Just if we show that every point of it has a locally compact, has a relatively compact neighborhood, then B will be locally compact. So let's start with any point of B. So let B any point of capital B, and this capital B is of the form O intersection C, isn't it? Where this O is open, this is important, and C is closed. C is closed in X. Okay, now B in this. So B in O, and O is open set in X, and X is locally compact Hausdorff. Okay, then this O is a neighborhood, open set containing B, so neighborhood is a neighborhood of B in X, because O open in X. So in the locally compact Hausdorff space, X. Fine. So by the result proved in cliff 8, we have characterized local compactness of a Hausdorff space. Okay, we have proved equivalence of 4 statements. By using that, we will get another. So there exists a relatively compact open neighborhood U, isn't it? It was written there. So there exists a relatively compact we are in X, okay, relatively compact open neighborhood U, very open set, open neighborhood U of B in X such that this B in U obvious, U subset of U bar also obvious, and U bar will be contained in O by that result, by that characterization, okay, proved in clip 8. Fine. So U is a neighborhood of B in X. So U intersection B will be a neighborhood of small b in B, right? So U intersection B is an NBD neighborhood of B in B is important, in B, and disclosure of this U intersection B, in B, this is U bar, closure of U in X intersection B, this is equal to this U bar intersection. Here is the place where we will use once again this expression, okay, O intersection C. Fine. And obviously, since U bar is totally contained in O, so this is totally contained in O, so this intersection will be U bar, so this is U bar intersection C, okay. Now this is closed in U bar because C is closed in X, so closed in X intersection U bar, closed in U bar. So this is closed in U bar, and this U bar, this is closed in U bar, and this, okay, which is compact because U is relatively compact. There exists a relatively compact open set U, isn't it, in X. So U bar is compact because U is relatively compact. Fine. So U bar, which is compact. Okay. So this is closed in U bar, isn't it? This is closed in U bar, and which is compact. So this is also compact, isn't it? Fine. Okay. So this implies, so its closure in B is compact. This implies this closure, this U intersection B is compact. Let me write this again. Fine. So closure of U intersection B in B is compact. So this is this neighborhood. U intersection B is neighborhood. It is done already. U intersection B is a neighborhood of B in B. I will show that it is relatively compact neighborhood of B in B, because we will show B is locally compact. Okay, it is done because this is the closure of U intersection B in B is compact. So U intersection B, which is a neighborhood of B in B, is relatively compact in B. So this is a relatively compact neighborhood of B in B is important. Fine. So and B is housed up because the underlying whole space is housed up. Okay. Fine. So B is locally compact. So done. Okay. So if B is locally compact, then B equal to O intersection C by the previous result. Now if B equal to O intersection C, where O is open, C is closed in X, then we see that B is locally compact. So a subspace of a locally compact Hausdorff space is locally compact if it can be expressed as a intersection of an open set and with a closed set. Okay. So the consequence of this result is very, very important. Okay. So a corollary of this result, or corollary, we should write corollary of this last result. It is open or closed subset. Open or closed subsets of a locally compact Hausdorff space are open or closed subsets of a locally compact Hausdorff space are locally compact. Easy consequence. Why? For let B be open or closed set closed in X. Okay. B be open or closed in a topological space. A set may be neither open nor closed. Okay. A set may be closed as well as open. But if B open or closed, then we know whole set is open as well as closed. Okay, since X is open as well as closed in X, and we can write B equal to B intersection X, then what will happen? what will happen? Just look at the last result. This if and only if B is of the form this O intersection C, O is open, C is closed. Okay, then B is locally compact. Okay, now if we consider that B is open, we will consider X as closed set. So open intersection closed. So B is locally compact. Again, if B is closed, then we will consider X as open set. So closed intersection open, that is open intersection closed. So again, B will be locally compact. Okay, so B is locally compact. So here we see a difference between one more difference between compactness and local compactness. In case of compactness, we know closed subsets of a compact set or compact space is compact. Open subset may not be compact, no. But here we see that open subsets of a locally compact vector space is also locally compact and closed also. Okay. So open or closed subsets of a locally compact Hausdorff space is locally compact. Okay, by using this, we will now in a position to explain that why a locally compact Hausdorff space may fail to be normal in general. Okay. Actually, I will give an example, and to understand this example, we need these results. Nothing new, you know this. Okay, so I am given an example for showing that a locally compact Hausdorff space may fail to be normal. So this is another difference between compactness and local compactness. Okay. Okay, so example is this. Okay, you know that S omega bar, that is S omega union the singleton omega. This S omega bar is compact. Okay, sometimes we write in this way 0 to omega. We have discussed during study of compact compact spaces in the regular class. Okay, we know this is compact, and by Tikhonov property, so S omega cross this S omega bar cross S omega bar is also compact. Okay, and it is Hausdorff. And it is Hausdorff. It is Hausdorff because every well ordered set with ordered topology is Hausdorff. Actually T4. It is Hausdorff because every S omega, well ordered, right? S omega bar well ordered. This is minimal, uncountable, well ordered set. Okay, every section of which is countable, and every countable subset of this S omega has an upper bound in S omega. This S omega with order topology, the S omega union this omega with order topology is compact. Okay, so and it is Hausdorff because every well ordered set with order topology is actually T4, so T2. So this S omega bar cross S omega bar, this is compact Hausdorff space, and we have proved in some clip, most probably 7th clip or something like this, okay, that compact Hausdorff spaces are locally compact. So this S omega bar cross S omega bar is locally compact. Fine, locally compact Hausdorff. Locally compact Hausdorff. Fine. Now, if we draw the rough case of this, so this including this omega, so this is S omega bar and this is S omega excluding this omega, okay, fine. Look at this. Now this S omega cross S omega bar, this S omega cross S omega bar, so it will be other from this roughly, okay, so dot. So this roughly speaking this square region without this side, okay, so this can be written as obviously this S omega bar cross S omega bar minus this side, this omega cross S omega bar, isn't it? This is omega cross S omega bar. Now this omega cross S omega bar, just a copy of this S omega bar, okay, just if we consider this map, this x, okay, this point say 0 comma x goes to omega comma 0 comma y, say 0 comma y goes to omega comma y, okay. So this map is continuous, okay, and this is compact is omega bar, so its continuous image is this, so this is also compact, maybe this is compact, and whole thing is Hausdorff, so compact subset of a Hausdorff space is closed, so this is closed, so closed set is deleted from this, so this is complement of this closed set in this, so this is open in this, okay. Now this is open subspace of the locally compact Hausdorff space, this S omega bar cross S omega bar. Now by this corollary of the results is open or closed subsets of a locally compact Hausdorff space are locally compact, so this is locally compact, so this open subspace is locally compact, so this S omega cross S omega bar is locally compact Hausdorff. Locally compact Hausdorff space. But we know, isn't it? We know it is not normal. It is not normal. During study of separation axioms, we have discussed. Okay, this is a locally compact Hausdorff space. Okay, but we know it is not normal. So a locally compact Hausdorff space may fail to be normal. Okay. So thank you for the time being. Keep watching. Okay. Thank you.